Grab an apple, a handful of dates, maybe a drizzle of honey in your tea, or even that glass of soda sweetened with high fructose corn syrup. You're looking at something most of us consume every single day, right? Fructose. We all know it as the sugar that makes fruit taste so good. But have you ever actually stopped to consider what happens inside your body the second you swallow it? How does your cellular machinery process this very specific type of sugar, and why is it such a massive deal for your health?
Well, welcome to today's Explainer. I am super excited to guide you through this because we're going to look at fructose not just as a sweetener, but as a fascinating biological rule breaker. While other sugars usually follow a pretty predictable path in your body, fructose, it basically operates on its own terms and completely bypasses your body's normal regulatory systems. Today we're unpacking exactly how fructose acts as the body's metabolic rebel, taking you on a microscopic journey from that morning bite of fruit all the way down into the processing plants inside your cells. So, here's our roadmap for today. First, sweet sources and absorption. Second, the liver's specialized pathway. Third, bypassing the traffic cop. Fourth, the liver versus other tissues. And finally, when fructose becomes toxic.
All right, jumping right into section 1, sweet sources and absorption.
To ground all this complex biochemistry in our everyday lives, let's start the journey in your intestine. When you consume fructose, it means a special doorway to actually enter your cells. It's absorbed through the intestinal wall using a very specific transporter called GLUT5. But here's where the story gets really unique. Instead of just circulating wildly all around your systemic bloodstream right away, it gets right onto a highly specific highway, the portal vein. This vein acts as a direct shuttle, rushing the vast majority of that fructose straight over to the liver. So your liver is essentially the primary organ burdened with catching and processing all of this incoming sugar.
Moving right along to section 2, the liver's specialized pathway.
Okay, let's dive into this. Since the liver is catching all this incoming sugar, it's developed a highly dedicated pathway just to deal with it. When fructose enters the liver cells, which are called hepatocytes, it's immediately acted upon by a specialized enzyme. The fructose is rapidly phosphorylated into fructose-1 phosphate. Then, it's quickly cleaved into two smaller molecules, DHAP and glyceraldehyde. Because this pathway is so dialed in, the liver acts like a super efficient factory, just churning through the fructose without waiting for any signals from the body. Honestly, it's a wildly rapid conversion process.
Now, to truly understand how that factory runs, we've got to meet the two VIP workers doing the heavy lifting here. First up, we have fructokinase. This is the enzyme found mainly in the liver that rapidly phosphorylates the fructose, effectively trapping it inside the cell as fructose-1 phosphate. Next up is Aldolase B. You can think of Aldolase B as the cleaver. It takes that fructose-1 phosphate and snaps it right into those two smaller pieces, DHAP and glyceraldehyde. These two enzymes are the absolute gatekeepers of hepatic fructose metabolism. Keeping their specific roles in mind is absolutely crucial for understanding the clinical disorders we're going to discuss a bit later.
So, what's truly fascinating is what happens next to those cleaved pieces. Once Aldolase B does its job, those intermediates have a few potential fates. They can be pushed into glycolysis for immediate energy, ATP. The liver can also use them to create brand new glucose, a process called gluconeogenesis, which can then be released into the blood, or they can be stored as glycogen. But here is the major clinical takeaway. Because fructose is processed so insanely fast by fructokinase, a high intake of fructose easily overwhelms the entire system. When there's just too much coming in, those pieces are heavily funneled into fatty acid and triglyceride synthesis. Basically, excess fructose promotes hepatic lipogenesis. You are literally turning that rapid influx of sugar straight into liver fat.
Which brings us to section 3, bypassing the traffic cop.
You might be wondering, why does fructose get converted into fat so much faster than regular old glucose? Well, in your body, the breakdown of normal glucose is tightly regulated by an enzyme called PFK-1. Imagine PFK-1 is a really strict traffic cop standing right in the middle of a busy intersection. When your body has enough energy, that traffic cop puts up a giant red light and stops the breakdown of glucose. It's slower, it's tightly regulated, and it's highly dependent on the hormone insulin. Fructose, on the other hand, takes a massive detour. It enters the pathway downstream, completely bypassing that PFK-1 traffic cop. It is totally insulin independent, so with absolutely zero red lights to stop it, its metabolism is exceptionally rapid and largely unregulated. And that is exactly why that sudden flood of energy has nowhere to go but to be stored as liver fat.
Let's look at section 4, liver versus other tissues. So let's briefly pause our liver journey to see what happens in the rest of your body.
While the liver uses that highly efficient fructokinase, your muscle and fat cells have to rely on an enzyme called hexokinase. And honestly, hexokinase has a very low affinity for fructose, mostly because normal glucose heavily competes with it. Because of that, fructose metabolism in your muscles is just a very minor pathway. On top of that, the liver has an enzyme called glucose-6-phosphatase. This allows the liver to package up newly made glucose and release it back into the bloodstream for the rest of the body to use. But muscle and adipose tissue, they completely lack this enzyme. So if fructose does somehow manage to get processed in a muscle cell, its energy is trapped locally. It's kind of like the Vegas rule. What happens in the muscle cell stays in the muscle cell. It cannot be shared back into the blood.
Finally, Section 5. When fructose becomes toxic.
We've seen how this specialized machinery works flawlessly in healthy individuals. But what happens when genetic defects actually break the machines? There are two primary disorders of fructose metabolism, and understanding exactly which machine is broken makes all the difference. The first is essential fructosuria. This is caused by a defect in fructokinase. Yep, that very first enzyme we talked about. If you lack fructokinase, fructose simply cannot be trapped in the cells. It just floats around and is harmlessly excreted in your urine. It's completely benign, no symptoms at all. But the second disorder is Hereditary Fructose Intolerance, or HFI. In HFI, fructokinase works just fine, but the second enzyme, Aldolase B, our cleaver, is defective. And this one is severe and life-threatening because it leads to a massive accumulation of a toxic metabolite right inside the cells.
And this brilliantly illustrates the exact cascade of metabolic failure in HFI. Because fructokinase is working perfectly normally, the cell rapidly pulls in fructose and burns ATP to attach a phosphate to it, creating fructose 1-phosphate. But because aldolase B is missing, that fructose 1-phosphate cannot be broken down any further. It hits an absolute dead end.
The domino effect this creates inside the cell is, well, a full-blown biological crisis. First, fructose 1-phosphate massively accumulates inside the liver cells. Second, because all of the cell's available inorganic phosphate is tied up in this trapped molecule, free phosphate levels absolutely plummet. Third, without free phosphate, the cell literally cannot regenerate ATP, so its energy levels drop dangerously low. And finally, because there is no ATP and no free phosphate, the liver's ability to break down stored glycogen, which is glycogenolysis, or make new glucose, gluconeogenesis, completely fails. The liver completely loses its ability to maintain blood sugar levels, and that leads to severe, life-threatening hypoglycemia.
Clinically speaking, this is absolutely devastating for an infant. Symptoms typically appear right after a baby is weaned from breast milk and introduced to solid foods like fruit, juices, or sucrose-containing formulas. The infant will experience vomiting, severe hypoglycemia, jaundice, and a failure to thrive. If left untreated, that toxic accumulation can rapidly lead to liver and kidney failure. But there is a very powerful silver lining here. The management of this condition is entirely dietary. With a strict, lifelong avoidance of fructose, sucrose, and sorbitol, these individuals can completely bypass that metabolic roadblock, resulting in an excellent outcome where they can live healthy, totally normal lives.
So, we've journeyed from a simple bite of an apple all the way down to the highly specific enzymes governing our cellular energy. We now know for sure that fructose isn't just some innocent sweetener, it's a metabolic bypasser. It is completely insulin independent, skips the traffic cops entirely, and drives the liver straight toward fat synthesis when consumed in excess. So, I want to leave you with this thought to ponder. Armed with the knowledge of how our biological machinery actually handles this rebel sugar, how should this change the way you look at your everyday food choices, especially in a modern diet overflowing with high fructose syrups and hidden sweets? Thank you so much for exploring the science with me on this explainer. Keep questioning and keep learning.